It's great to see so many people here. It's a great honor and privilege to welcome Jim Peebles to give us some reflective remarks about his life in physical cosmology. He literally wrote the book on the subject, so I'm not going to make a long introduction. One thing I do want to say is that there are many young people in the room, and they should feel very welcome to ask questions from Jim after his lecture. Please join me in welcoming Jim.
Thank you for those kind words. Colleagues, I propose to recall some of the events in my history and then offer what I consider to be lessons of broader application from what happened to me. So, to understand my story, it's helpful to understand the situation I encountered when I arrived at Princeton University as a beginning graduate student in 1958. Here to your right, you see Professor Robert Henry Dicke, Bob to all, who a year or so before I arrived, had decided that the physics of gravity was sadly neglected as an experimental field, and he determined to use modern technology to repeat old gravitational experiments and do new ones that had become possible. To the left in this image is David Wilkinson. He became the experimental leader in Bob's group, and I, in the center, became the theoretical leader. I offer an illustration of what was going on then, but first let's recall Bob. You see on the left, far left, his PhD dissertation at the University of Rochester, rushed to finish as he then went to the radiation laboratory on the east coast of Massachusetts, where he did raw research in radar. He returned to Princeton University. You see that first there is a list of these theses are roughly in order, chronologically. You see the theses on quantum optics and all that. You see the abrupt change mid-career to research on gravity physics. It's interesting that he also, like Nobel, loved patents. There is his book of patents on the far right. An example of the sorts of experiments that were going on is worth considering. If you want to measure the acceleration of gravity, centimeters per second, you might consider a parallel plate Fabry-Perot interferometer, and you know the amount of light transmitted is a function of the separation in units of wavelength. So suppose you drop one of the plates and count the fringes as they pass, bright, dark, and time them. Not practical because you'll never keep the plates parallel, so use a corner reflector. That's the device you see illustrated. Radiation coming in is reflected back in just the opposite direction. And so you see from a student newspaper a falling corner reflector, lots of experimental details. Here is the graduate student, Jim Fowler, whose doctoral dissertation this was. Here you see that if you go on the web to the Micro G Lacoste Corporation, you can buy one of these devices. You see the falling corner reflector, you see the interferometer. This thing is so sensitive that it can detect the change in gravity when you start pumping water from an underground reservoir of water and lower the water table. At the end of the Ice Age in North America, the northern edge of the North American plate was relieved of a great weight. It started rising. It's still rising. Florida, consequently, I've never been told whether this is true, but it's got to be sinking a bit, and that's causing extra problems along with rising sea level. But one of these gadgets placed in the northern part of North America will see the acceleration of gravity decrease as the plate moves up. I searched this website carefully. I could not find the price of one of these devices. Perhaps if you have to ask, you shouldn't. So I recall well when I was introduced to the notion. First of cosmology, and second of the notion of a hot early universe. This is the old physics building. Bob Dicke drew three of us together, Peter Roll, David Wilkinson, and me, offered an explanation of why he thought it would be neat if the universe began as a hot state in which it would contain thermal radiation. And he remarked that as the universe expands, the radiation is decompressed. It will cool, but it won't go away. If the universe is homogeneous, there's no place to go. He suggested that Roll and Wilkinson build a radiometer, a microwave radiometer, to see if they could detect this radiation. And he said, I think very casually to me, look into the consequences of finding or not finding the radiation. So Peter Roll went off to education, and David and I continued to follow Bob's advice through our entire careers. At the time, well, okay, Bob had lots of interesting ideas. I didn't think there was any more than just another of them. And in fact, I was very uneasy about the notion of spending much time on cosmology. Let's recall that in the mid-1960s, it was a pretty schematic subject. It was a real physical science in the sense that there was a theory, there were two theories, there were observations, and there was research in progress to try to improve both, but the research was at an almost standstill. So I was, why am I spending much time on this? Well, I was encouraged by the consideration that from Hubble's constant h, and from the top line, you can get a characteristic expansion time, around 10 to the 10th years. You can form, by dimensional analysis, a characteristic mass density, h squared over g. You are marrying cosmology, the expanding universe, with gravity, and you're getting a density that is, well, roughly what you would expect from the masses of galaxies and their number densities, as well as the time. That is not out of line with stellar evolution ages. Of course, if you go a little more and you add to gravity, Planck's constant, you get an obscene mass density that surely is ridiculous. That is nasty. But the other two, it did encourage me to think that perhaps there is something in this. Though I must say, I didn't know why we assumed the universe is homogeneous. There was not much evidence of it at the time. It was more taken as an easy working hypothesis, I think. So, following Bob Dicke's advice, I looked into what might happen if the universe did begin in a hot, dense state. It immediately occurred to me that when a pressure cooker explodes, things are scattered about, and they're scattered about with different degrees of cooling. So you might expect that the baryons would end up characteristic of a wide range of thermal equilibrium, thermal temperatures. So I worked this out, and you see the evolution. Time is increasing toward the right in the early universe. Neutrons and protons are near in thermal equilibrium in their abundance ratio. As the temperature falls down to around 10 to the 9th K, the neutrons and protons can combine to form deuterons. You see the abundance of deuterium increasing. Once there is a fair number of deuterons, they start reacting with each other through particle exchange reactions to make helium. Here is a possible consequence of a hot Big Bang. I also recognize that the experiment might very well end up with a negative result. The universe began cold. If the universe were cold, there would be an interesting problem. The degeneracy energy of electrons would make it favorable to squeeze electrons onto protons to make neutrons. A sea of neutrons would be unacceptable because as the neutrons decayed, they would make protons. Protons and neutrons would combine to make deuterium, and you would end up in a universe with not much hydrogen. That had to be avoided. Of course, the obvious way around that, postulate degenerate sieve of neutrinos. It's a fascinating point that in the Soviet Union, Jacob Zeldovich at the same time was thinking about an expanding universe. He knew of Gamow's results on this subject. He felt that Gamow was on the wrong track because he felt that the oldest stars contained little helium. If so, then the hot universe is in trouble. let's imagine a cold universe. And again, he said, let's postulate degenerate sea of neutrinos. On the other hand, I was not aware in the mid-1960s that George Gamow had invented many of these ideas a decade and a half earlier. Again, I had been reinventing the wheel. Here are two examples that fascinate me. In each case, two individuals, well separated, not speaking to each other, nonetheless arrived at two concepts at the same time. First, that if the universe were cold, you'd need a degenerate sea of neutrinos. If it's hot, you would look for a lot of helium. It's an example, I think, of what happens is when the time is right, there may be independent recognitions of a particular line of research. So, here is David Wilkinson holding the screwdriver, Peter Roll standing behind the Dicke radiometer. They're building it. Meanwhile, and 5 years earlier, at the Bell Telephone Research Laboratories, not far from Princeton University, engineers are working on developing microwave communications. What gave us these cell phones whose use so troubles me as I see students wandering the streets looking at their cell phones. This is the beginning. You notice this early experiment is quite crude. See the planks, so they're just rough, supporting an antenna that is not at all rough. It's a very sophisticated design meant to very strongly resist radiation from the ground. They encountered a problem with this instrument. Inside that shack were very sophisticated traveling wave maser amplifiers whose properties were well understood. The engineers building this machine and testing it could compute the expected production of noise in microwave radiation all along the path to the output of the maser. They found that when they did the sums, they had to postulate that about 2 degrees of noise was originating from the ground. They surely know that that is quite wrong. The antenna rejects side lobes and back lobes better than that. They had an anomaly. That anomaly remained a dirty little secret at the Bell Telephone Laboratories until 1964, when two young people who had joined the laboratory, Arno Penzias on our right and on our right, and Bob Wilson on the left, resolved to find the source of this excess noise. They are to be credited for refusing to give up the search for that noise originating either in the instrument or coming in from the local environment. And furthermore, complaining about the problem until someone heard them and told them they really ought to get in touch with Bob Dicke. That gave us the recognition that there is a sea of microwave radiation. I've been asked many times, so what did you think when the connection was made? I don't remember any sign of regret over being scooped in the detection of this radiation. I instead remember excitement over the fact that this experiment, which you know was simply a blind guess, would the universe have radiation or not? There is radiation. It may be explored experimentally, and it may be studied theoretically. I remember excitement. I also can tell you how we got together. Oh, yeah. So here, let us review how it happened that okay. I was getting invitations to give colloquia on my research with the hot Big Bang theory. I asked David Wilkinson if he minded if I told him, if I gave colloquia on the search for this radiation and my ideas about how to interpret it. I remember well his words, sure, go ahead and talk about this. No one could catch up with us now. What he didn't realize, of course, none of us, we had been caught up with earlier. The radiation was there to be recognized. First colloquium I gave on this subject, Wesleyan University, Connecticut, nobody paid any attention. I showed this graph on the left showing what was known about radiation in the universe, if we have a homogeneous universe. Upper bounds, measurements at higher frequencies, and two thermal spectra. you see an upper bound of 3 centimeter. None of us can recall where I got that number. On the right, you see an upper bound in the graph I showed at the Applied Physics Laboratory at Johns Hopkins University, an upper bound at 6 centimeters. I cannot recall where these came from. The triangle on the right-hand plot is what became known as the Greisen effect. If there were a sea of gamma rays with energies in the frequencies around 10 to the 12th hertz, their mean free pass, we have energetic cosmic rays. They move at relativistic speeds through intergalactic space. If there is a sea of radiation in the band indicated, then the interaction of the radiation with the high energy cosmic rays would cause photopion production, particle production, which would slow them. So we could put a bound on what can be there. But in February of 1965, I gave a colloquium, as I say, at Johns Hopkins University. Ken Turner, a good friend from graduate student days, attended that colloquium. He told Bernie Burke here, with on our left, Alar Tourmey, on the right, George Clark, X-ray physicist, and we had the answer. Here is my first book on cosmology, 1970. Here on the right, you see what was known about the sea of radiation at that time. You see how ready the community was to study this radiation. Within a few years, you see in the middle at 3 centimeters, the Princeton experiment, 7 centimeters, the Bell Lab measurement, and the others filled in over a considerable range of wavelengths and a relatively promising fit to a thermal spectrum. You see also a apparent anomaly, that little triangle. Those anomalies continued to be present for another 20 years. I hated them. I didn't want to think about radiation. You see, you could understand where that excess radiation could have come from. Perhaps the universe is not exactly homogeneous. If different regions started with different temperature, we would see a mixture of thermal spectra. That would be at the long wavelength limits, the really genes form, but at short wavelengths it would be higher because of the mixture of different temperatures. You could also imagine wildly energetic events in the early universe that released energy and produced that excess radiation. The situation became clear only in 1990. Whenever I talk about this radiation, I have taken a solemn vow that I will show photographs of the two groups who showed that the spectrum is thermal. Here you see, do we have a pointer? No, never mind. You see John Mather, the tall guys in the middle, in the back. Nobel Prize for showing that the spectrum is thermal. George Smoot, far left with all the hair in the back. Nobel Prize for detection of the first departure from exact homogeneity. Further to our left, in the front, Ray Weiss, Nobel Prize for detection of gravitational waves. He was the central figure in LIGOs. Other people in there are of that class. This is a remarkable group of people. Here is another group led by Herb Gersh, University of British Columbia in Western Canada. Here are his two capable assistants, Mark Halpern and Ed Wishnow. This is my favorite photograph of scientists at work. If you didn't know that they had done something truly remarkable, would this photograph have inspired confidence? So, here are the two results. The NASA experiment has much better accuracy, much smaller noise because they could integrate for a long time. The UBC, the British Columbia experiment on the right, more noise, but either of them shows the effect. The spectrum is close to thermal. The NASA experiment was announced. Both of these experiments took some 15 years to complete. They were completed within the space of 2 months. The NASA experiment gained from that 2 Nobel Prizes. The UBC experiment, well, it didn't get anything except the respect of their colleagues. While I was waiting to learn whether the spectrum is really thermal, I decided that it would be interesting to have measures of the distribution of galaxies, because after all, if you measure something, you may discover something interesting. It was as simple as that, the notion, since galaxies are out there, and since there are catalogs that measure how the galaxies, that have the data on how galaxies are distributed, let's see if we can make statistical measures of that distribution and see whether it suggests something. As it happens, that turned out to be the case. So here you see, below that thick computer output on the top, copies of notebooks on the counts of galaxies in small 10-minute by 10-minute squares running across the sky. These data were obtained by Donald Shane with the assistance of Carl Wirtanen, and a few others. Here is Donald with some graduate students from Princeton University. It's been my experience that when something interesting is happening, graduate students will cluster around. It certainly happened here. So Donald Shane took 10 years with traveling microscope on photographic plates to count galaxies in little squares, 10 minutes by 10 minutes, over much of the sky. He got roughly 1 million cells. The data are where, as you see in that pile, what can you do with 1 million numbers before the age of high-speed computers? Well, high-speed computers came along at that time. I, with the aid of these graduate students, Bernie Siebers is off scale, could take these data and analyze them and see what is there. I like images, and so I was pleased to make this as an image. It's a section of the distribution across the sky of the galaxies that Donald Shane and Carl Wirtanen were measuring. I had the distinct pleasure of showing Donald Shane this image and asking him, "So is this what you saw?" He laughed and said, "I was looking at this one galaxy at a time." We could, of course, do statistical analyses indeed. A two-point correlation function is the obvious thing you would do to start. And it occurred to Nelson Limber, as these data were being taken, that it would be good to measure the two-point correlation function. I draw your attention to how he did it. He took the counts of galaxies summed up in 1-degree cells across a line of constant declination. He then took the same data on a strip of paper and another strip of paper of the same numbers, that he split one strip relative to the other by theta degrees, phi degrees, multiplied down and summed to get a two-point function. That's a good estimate, but terribly laborious. And in fact, it doesn't use the data because he's only correlating in one direction, not two. We had, as needed, the digital computers that will allow us to do this analysis. Here, one of the high points of my life. Different catalogs reach different depths. The greater the depth in a statistically homogeneous universe, the smaller the clustering, because you are seeing clustering on top of clustering. The two-point correlation function scales with depth in a way you can compute. And so from 3 catalogs at different depths, the bottom one, Fritz Zwicky's catalog, the middle one, Donald Shane's catalog, the top one, no, sorry, I got it the other way around. The top one, Fritz Zwicky's catalog, the middle one, the Lick catalog, the bottom one, the Jagiellonian field obtained in Poland. 3 different depths. Apply the scaling relation for how the autocorrelation function should scale with depth. You get the curve on the right, and you see within pretty good accuracy the 3 are consistent. That would not be the case if the clustering, for example, were seriously affected by obscuration that is patchy across the sky. It was then evidence that we have a true measure of the galaxy two-point correlation function, the autocorrelation function. Here is an example of a book I wrote on that subject, The Large-Scale Structure of the Universe, full of all these details. Lovely statistical considerations. I loved it. What is striking to me now is that here in 2019, this book on such considerations is near 40 years old. But if you should go to Princeton University Press and order a copy, you will see a little sign on this 40-year-old book. So, another thing that occurred to me when Bob suggested I think about the theoretical significance of a hot universe is that in the early universe, the baryons will be thermally ionized. We will have a plasma. In that plasma, the free electrons scattering off the radiation will cause radiation and plasma to act as a viscous fluid. A viscous fluid that's slightly inhomogeneous will oscillate. The oscillations have a boundary condition that when the temperature is dropped to about 1,000 degrees, the plasma will combine to neutral atoms that will eliminate rather abruptly the oscillations of the radiation. And of course, that means you put in a temporal boundary condition, and that means that the modes of oscillations that are favored have discrete wavelengths. On the left, you see a computation of a given Fourier mode amplitude as a function of time. The mode oscillates, that's acoustic oscillations. It then starts growing when matter and radiation decouple at recombination. I have a puzzle. I don't remember making that plot on the left, but it's there marked in our files, October 1968. I guess I must have. Or unless Jeremy you made it. Anyway, on the right you see the resulting power spectrum of the distribution of matter after decoupling. This effect is observed now. It's rather striking. Who knew back in the late 1960s that this effect would be detected? I certainly didn't imagine that. I just did these computations because I found them interesting. I notice also, here's an illustration. That power spectrum for the matter distribution looks sort of like a series of bumps, more or less uniformly spaced. The Fourier transform, of a sine wave is a delta function. The Fourier transform of that series of bumps is something like a bump. Well, you make the Fourier transform and you get the results indicated on the left-hand part. Depending on the cosmological parameters, you get a bump of different shapes and at different linear scales, but you get a bump. Here, that's 1981, 2005, that's 25 years ago. 25 years later, the bump is seen. Of course, the bump is in a different place because we didn't have dark matter then, but the effect was predicted, and who knew? It's there. What else? Well, here's Jerry Yu with Bob Dicke and David Wilkinson. And what do we have next? Bob Dicke, Dave Wilkinson, and me in front of, behind this device, which went up in a balloon. And to measure small departures from uniformity in the radiation, a good way to go is to have two antennae, like so, and to rotate them and take the difference of radiation detected in the two detectors. That's the technology that was used in later satellites, including WMAP. As these experiments grew more and more precise, there became a greater and greater problem. The galaxy distribution is quite manifestly inhomogeneous, clumpy. The radiation distribution, well, you see here the nature of the distribution, but what you don't see is that the mean has been subtracted and that in the lower figure, the fluctuations are departures on the order of parts in a million. The radiation is wonderfully smooth. In the early 1980s, the limits were much poorer than these detections, we knew that the radiation isn't more inhomogeneous than a part in 10 to the fourth running across the sky. But even a part in 10 to the fourth is really miraculous considering how clumpy the galaxy distribution is. How could it be that galaxies grew and clusters of galaxies grew without disturbing the radiation? You see, the immediate problem you have is that the radiation is ionized, and the matter is ionized in the early universe. That means that as it moves around to gather into concentrations, it's going to pull on the radiation. How do we prevent the radiation from being dragged by the matter? Out of desperation, there's only one solution: postulate that most of the matter is not baryonic, that it does not interact with radiation. That is an ad hoc assumption out of desperation. So, what did we do? I was pleased to see, well after the measurements, that back in 1982, I had predicted that in this universe that is dominated by dark matter, not a term I invented, but by matter that is not interactive with ordinary baryonic matter or radiation, the quadruple anisotropy 3.5 parts in a million, the WMAP satellite, which is arranged to do this, detected this anisotropy 5 plus or minus 1 times 10 to the minus 6. I don't know whether that plus or minus is a standard deviation, but if it is, I was off by 1.5 sigma, so not bad. Dark matter. The power of ideas. Through my career, I have experienced the power of ideas. In particular, consider that in general relativity theory, the top equation is a fairly general description of how the universe might evolve. A source for the rate of expansion of the universe is the mass density. Another source is space curvature. And yet another source is Einstein's cosmological constant. The Einstein de Sitter value does away with both space curvature and lambda to get the second equation. That is a particularly elegant situation for the following reason, you will recall. At some point in the evolution of the universe, we evolved, came on the scene, took an interest in how fast the universe is expanding. Are we at a particular epoch or at some random time during the course of evolution of the universe? If the Einstein de Sitter model applies, then whenever we happen to flourish, we would find that the universe is in effect expanding at escape velocity. That's what that bottom equation says, escape velocity, no matter when we come on the scene. If either space curvature, the radius r, or cosmological constant were present, then at different times you would find that the unit expansion is close to escape, at other times that the expansion is very different from escape. Surely we don't live in a special time. Surely the universe is Einstein de Sitter. What's happening here? Oh, it's in there. It seems to have reappeared. I don't remember why. Inflation. Early 1980s, just as it was needed, the idea that the universe is close to uniform because there was a time in the early universe when the expansion rate was very rapid. So rapid and the expansion so great that all irregularities in the universe were stretched out to very large scales so that the part of the universe we can look at is very close to uniform. A beautiful idea. Of course, that great expansion that irons out irregularities would also make the radius of curvature of space sections extraordinarily large, so we can ignore r going to infinity, 1 over r squared going to 0. We could ignore space curvature. And of course, lambda is ugly, so we'll ignore it. We believe it has to be Einstein de Sitter. This line of thinking is no longer quite accepted, but never mind, that was the thinking in the 1980s. If the universe is at all sensible, it's Einstein de Sitter. It took a long time to convince people that what works is a universe with Einstein's cosmological constant. Impressive then that inflation convinced the community that there should not be space curvature. Considerations of elegance convinced the community there should not be lambda, so we got one out of two right. Another problem now with the mass density. Before the experiment discussed here, before 1983, well, I knew about this in 1982, I went along very much with the idea that the universe surely is Einstein de Sitter because it's simple. I was more than a little shocked when Mark Davis completed his first systematic redshift survey. He invited me to join the analysis of that redshift survey. The analysis showed us that if mass is distributed in the same way as the galaxies, then the cosmological parameter that represents the mass density is well below unity. The universe is not Einstein de Sitter. I was shocked, but I decided to learn to live with it. The community did not welcome that decision, and they said, surely this means that the matter is not distributed in the same way as the galaxies. There are a lot of arguments back and forth over whether that is true, but here's the central thing that really impressed me. The notion of biasing was that galaxies form more likely, the galaxy formation is more likely where the mean mass density is higher than average. That would mean that where the mass density is low, you have fewer galaxies. That would mean that the galaxies are more strongly clustered than the mass, and that's what you want if you want to live in an Einstein de Sitter universe. This figure from 1982 is what made me very doubtful of that situation. For you see in these two panels the angular distribution to a fixed limiting depth of low luminosity galaxies and high luminosity galaxies. I remember with Mark Davis looking at these two and asking, well, which were the luminous galaxies and which the faint? These look so remarkably similar. I'm still struck by the similarity of those two distributions. That's not what you'd get if biased galaxy formation occurred according to the ideas of the time. I spent then quite a bit of time as a Cassandra in the cosmology community at conferences saying, look, you're discussing an Einstein de Sitter universe, but it doesn't look like that's the case. I remember still a bright young student who I will not mention saying, you're only doing this to annoy. Indeed, I knew it teased, and that pleased me, but I meant it. It doesn't look like our universe is Einstein de Sitter. Here's a collection, actually, of the situation up to the year 2003. There are lots of ways to measure the mean mass density. Each of them is subjected to systematic errors. But the remarkable thing is, by and large, none of them likes Einstein de Sitter. Across many ways to look at the universe, we are driven, I think, to the conclusion that we live at a special epoch. Make of that what you may. So, what is this saying? If we want to save flat space sections, and we want to save special general relativity theory, and if we want to save the evidence that the mass density is less than critical, we need Einstein's cosmological constant. I pointed out earlier that quantum physics does not fit at all well with gravity. But nonetheless, we're going to have to live with it. We need a cosmological constant. I might remark by this time, the community was growing, and it had grown large enough that there were a few brave people who started to accept the arguments that the mass density doesn't seem to be high enough for Einstein de Sitter, and that maybe we need a cosmological constant. It's another case, I say, of the time being right. Well, the big revolution in cosmology occurred at the turn of the century by two magnificent sets of experiments. First, the dream of Tolman in the 1930s. Let us measure the relation between the redshift of an object and its apparent magnitude, given that the objects have a common luminosity. the redshift magnitude relation. Tolman worked it out in the 30s. In around the turn of the century, 70 years later, supernovae were said to be standard candles. The measurements of supernovae as a function of redshift out to redshift 1 shows on the left the redshift magnitude relation. The dotted line, the dashed line, Einstein de Sitter. Lower the mass density, but keep the cosmological constant 0. You get the dotted line. Better fit still, add the cosmological constant. On the right, a figure that I'll return to in a few moments. Mass density on the horizontal axis, unity means you have Einstein de Sitter. 2 means twice that mass density, 0, no mass. And vertically, the cosmological constant defined in a similar way. The diagonal line increasing upward to the left, cosmologically flat universe. You might notice that in these data from 2000, really, you could get away with a mass density, let us say 0.2 times critical, and 0 cosmological constant. You'd fit just inside the outermost of those ellipses, but by 2003, in fact, that even was excluded. Evidence that you need a cosmological constant. But you know, if this had been the only data showing us experimentally that there is a cosmological constant, then my theory is the community would have divided into 3 camps. One camp would have pointed out that that solid curve, which is, the solid curve, gives very close to the prediction of the steady state theory. You should be impressed that the steady state theory made a prediction back in the 1940s that is close to what is measured 60 years later. Why aren't you paying attention to that? Of course, the answer is simple. You look at high redshift galaxies, they don't look like the galaxies we see around us. That theory is not going to survive. People have been offended by the fact that we have been ignoring the prediction of the steady state theory, but you have to bear in mind that there's more evidence than this, and the steady state theory just doesn't work. A second class would have said, well, all right, I'm going to learn to live with lambda. The third camp would have been, I think, you are assuming that you can compare supernova at redshift 0 with supernova at redshift 1. How do you know that they're really statistically equivalent? My bet is that if this were the main evidence for lambda, we would have many who say, you've made a systematic error in applying the redshift, in applying type 1a supernova. But as it happens, nature sometimes is so convenient. There was another great experiment, the anisotropy measurements of the microwave background radiation. You see in these panels again, mass density along the horizontal axis, cosmological constant vertically, the solid line, cosmologically flat. The situation in 1997, upper left, a rough indication that, well, maybe these parameters are getting constrained. In B, in 2001, the supernovae are the orange and yellow bands. Let's concentrate on the blue band. That is what is allowed by the lambda CDM cosmological model fitted to the anisotropy measurements. Notice the beautiful fact that the measurements are favoring something around cosmologically flat, though they are allowing a considerable range in the mass density if you're willing to adjust the cosmological constant. 2002, just before the flight of the satellite WMAP, the constraints from Ned Wright, published later, but this is a situation in 2002. You notice that you could, and you notice the colors give you another parameter, the Hubble constant. So you could learn, in 2002, we could live in a universe that is Einstein de Sitter, omega matter equal 1, omega lambda equals 0, but to do it, you would have to postulate a Hubble constant down around 30 or 40. That situation was in fact endorsed in papers, but it was hard to imagine that the astronomers were so far off in their estimate of the cosmological constant. The WMAP satellite flew, and you get the lower right-hand figure, where now you just can't find a value of the Hubble constant that will give you Einstein de Sitter. And you notice that a sensible value of Hubble's constant, around 50 or 60, intersects that flat line at a universe with about 30% dark matter and 70% lambda, consistent with what the supernovae were telling us. Two measurements, quite independent, different chances of systematic error, yet giving us a consistent story. That was really strong, persuasive evidence that we're on the right track. And here, just to bring you up to date, here are the acoustic oscillations that I mentioned, leaving a trace both in the distribution of matter on the left and the distribution of radiation on the right. The oscillations, a result of the boundary conditions imposed on the acoustic oscillations by decoupling, and of course the start of expansion at high redshift from homogeneity. The same parameters in the theory of cosmological cold dark matter plus lambda plus traces of baryons gives the solid curves in both figure. You can't, well, the solid curve in the left, the dash curve on the right that's totally lost among that magnificent swarm of data. The same, these are measurements of the universe in two quite different situations, low redshift and high, measured in quite different ways. They're giving us a consistent story, surely strong evidence that this is a good approximation to the way the world is. So I've decided that, now we will pause for a bit of shameless advertisement. These are copy-edited manuscript for a book. Its title is Cosmology's Century. It will be available next spring, $40 US, not so expensive. It will tell you more about all of this stuff. And it includes some thoughts on nature, the nature of the enterprise of natural science. These are lessons drawn from my experience in cosmology that I hope have slightly broader, somewhat broader application. Number one lesson, let's recall that natural science operates on a postulate, that nature operates by rules we can discover. No one ever told us that. No higher being came down and said, look, you can find rules. That's a made-up idea. Of course, it works wonderfully well. Second point, beautiful ideas can deeply influence the search for these rules. I consider the prime example of that the fact that Einstein's general relativity theory was accepted by and large without much debate when the evidence, when the experimental tests of general relativity theory were so very limited. Consider, now I drew a quote from Martin Rees because he is a great enough scientist that he can stand a bit of teasing. In particular, 1984, he wrote, "The evidence for hidden mass is incontrovertible. You can't deny it." Of course, that evidence interpreted required the inverse square law of gravity. It was applied on scales, well, he says, from 10 kpc to a few megaparsecs. Let's choose a third of a megaparsec. That is 10 to the 24 centimeters. Let's consider that the precision tests of general relativity theory on the scale of the solar system are probing scales of around 10 to the 13 centimeters. You're extrapolating the theory by 11 orders of magnitude in length. You might ask yourself, would you trust an extrapolation of 11 orders of magnitude in anything? Yet we did. The power of a beautiful idea. beautiful ideas can work. General relativity theory now has been subject to searching tests on the scale of the observable universe, and of course on the scale also of the laboratory. It passes all tests. But consider the next lesson. There are more beautiful ideas in this world than there are universes for us to explore. We have only one. These beautiful ideas can't all be right. Beauty can mislead. Consider the Einstein de Sitter universe. It is really the universe I would choose if given the chance, but of course it isn't the universe we have. Consider fractal cosmologies. Benoit Mandelbrot, a genius, he took the idea of clustering hierarchies, gave it a name, fractal, and pointed out all kinds of applications. He was deeply influential for good reasons. Time and again in physics, people are finding fractal behavior. I illustrate, we did this whole room over in fractals. But this is not a fractal. That part and this part look similar. It's not a fractal. It was, for a time, a remarkable phenomenon. At conferences, we would have talks on fractal universes. But we had this, a beautiful idea that doesn't work. Ugly ideas can sometimes work. Consider Einstein's thinking about his cosmological constant. I will read to you. This is a letter to Georges Lemaitre, slightly post-war, 1947. There is a book being organized, The Philosophy of Albert Einstein, something along that lines. Lemaitre is writing in it. He writes to Einstein, trying to persuade him of the merits of the cosmological constant. Dear Professor Lemaitre, I thank you for your kind letter, etc., etc., etc. Since I have introduced this term, I had always a bad conscience. And toward the bottom, I cannot help to feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature. Well, more lessons. The sociologists got a bad reputation by pointing out that since physics is done by society, physics is a social construction. How can you deny that? But then there is the following thought. Another society with different culture might invent another theory. And then the two theories, a better ordered society might have a kinder, gentler theory. But of course, we dislike that thought because after all, we have a lot of experimental evidence that shows that our theory is in the right direction. But now bear in mind that the lambda CDM cosmology is incomplete. That's nothing special. I put it to you that all physical science is incomplete, right, across the board. Cosmology is particularly incomplete because we have such things as dark matter and dark energy. We don't know how the world began. We have ideas, but we don't know. I think it is therefore entirely conceivable that another culture might have come up with another theory that is better than lambda CDM, because surely there is a theory that is better than lambda CDM. But I think it's also an excellent bet that that theory will look a lot like lambda CDM, including something that looks a lot like lambda and something a lot like dark matter. More thoughts. The role of society in determining the way science progresses. The example that everyone knows, I think, Darwin and Wallace on natural selection. I imagine in England, I don't know anything about these two characters, except I can imagine as youths, they collect beetles and pin them to cardboard. England is busy surveying the world, looking for commercial opportunities. They send along naturalists, including Darwin and Wallace. The naturalists noticed that, for example, in an island in the Galapagos, the tortoises look very different from another island, and the finches look different. Wallace up in the far east, noticing the islands, well separated, have flora and fauna that look systematically different. Here was a case where people were set up to discover natural selection, and no surprise, therefore, the two people independently, as far as I know, discovered it. Consider, though, the WIMPs, the original notion of the dark matter that we had. It was introduced in 1977. I was startled to learn that 5 groups independently came up with the notion that there is a 4th neutrino family that has a mass of around 3 GeV that would amount to an interesting mass density today. Here they are listed. The 5 papers were submitted to journals within the space of 2 months, as you see. The publication dates scattered widely, the usual range. I have checked with Pete Hutt, Steve Weinberg, and Rocky Kolb that they didn't know the astronomers' evidence that there is dark matter around spiral galaxies. They had the vague notion that the Einstein de Sitter model is kind of interesting. They all pointed out that these neutrinos, what became to be called WIMPs, would have a mass density that is about Einstein de Sitter. But that's all they knew. How did they each decide that this is an interesting idea in so short a time? I don't think they were talking to each other. I have the impression that instead there was the idea in the air. Well, first, of course, the Tau family was just being discovered. It has a neutrino that could be quite massive. The WIMPs couldn't be that neutrino, but if you can have a massive neutrino for taus, what about a supermassive neutrino for something else? Ideas in the air. And they proposed it. 5 years later, I used it. Consider also the burst of energy after the Second World War. A horrible conflict, but it released an amazing amount of energy in arts and sciences after the war. How am I doing for time? Well, I offer you 4 cosmologists in alphabetical order: Bob Dicke, George Gamow, Fred Hoyle, Yakov Zeldovich. The intuitive genius in this class is George Gamow. His 1948 papers are just a gem of intuitive physics. But along with his deep intuition was his deep disinterest in details. He didn't create a research group that lasted. He didn't work out details. He went on to other things. Fred Hoyle, brilliant in the physics of stars, brilliant in his introduction with others, with Gold and Bondi of the steady state theory. But from my few discussions with Fred Hoyle, I got the clear impression he felt that the scales of cosmology are so vast that you will never establish an empirically based cosmology. It must be based on philosophy. He was unable to bring himself to accept that we were developing an empirically based cosmology. Bob Dicke and Yakov Zeldovich both came out of war research. Both at about the same time started research groups in gravity physics and cosmology. Why did they both decide this? Well, at least we have the hint, the burst of energy after the Second World War. Bob's research group still lasts. I reckon it's in its 4th generation of leaders and going strong. Zeldovich's research group broke up with the breakup of the Soviet Union. Otherwise, they were quite similar paths. And finally, well, no, let's go on. Why did society agree to pay my salary all these years? What I was doing has no commercial application. My theory is, well, okay, I propose, I'm running out of time, but I must say this. Many of you, perhaps all of you, have locked eyes with a baby just old enough to be able to hold its head up. Do you not think that that's an uncanny experience? Your eyes are locked on the baby's eyes are locked on yours. And you ask yourself, what in the world is that baby thinking? So my theory, which I've discussed with a few psychologists who debunk it instantly, the baby is wondering what is going on. A deep primal instinct to know what is happening. And I submit to you that we as scientists are driven by that same consideration. What in the world is going on? We serve society by addressing that question. Next, there is the remark of the noted American philosopher and expert on baseball, Yogi Berra. You can see a lot by just looking. Here are examples of people in cosmology who contributed to this subject by just looking. I have one final remark. This week has been unworldly for me. And finally, I came down to earth this morning when our hotel door slowly opened in the dark room, in came Lucia. It was just a beautiful experience, gorgeous. I came down to earth. I thank Sweden for that, and I thank you all for your attention.
Thanks very much for that inspiring and amazing talk. We have time for questions. Who will start? Okay, I'll set things off. So you talked about the difference between ugly ideas and beautiful ideas, and also the sociology that might actually lead us to classify things as ugly or beautiful, even though nature doesn't think about it that way. Do you have any thoughts about, whether beautiful ideas get reclassified as ugly or vice versa?
There is the trait, surely adaptive, to find beautiful anything that works. I think quantum mechanics is not a beautiful theory, except for the fact that it's wonderfully beautiful because it is so powerful. I don't know. Why are we so pleased with the shape of a spiral galaxy? Our ancestors grew up avoiding the tigers and eating the mice or whatever they did. They didn't experience galaxies, yet we look at them and we're pleased. Somehow, nature pleases us, even in areas where we have never had the experience.
There's a question over there.
No. I realize, well, no, I feel indeed very lucky to have fallen into a situation to do what I love. I learned that I love physics at the University of Manitoba. I learned first that there is a profession of physicist and that one can make money at it, and that it is a beautiful thing for me to experience. I needn't have gone into cosmology. As I said, I, for quite a few years, felt sure that I would soon stop doing this and start doing something real. But no, one thing after another kept me going.
More questions? Yeah, this one here.
Yep.
It's pretty amazing to see just how much is out there. It feels like there's a long road with no begin. I don't know cosmological.
You know that.
I suppose my question is, how would you suggest going about it? Like when you were a student just starting out, did you try to keep up with the science, or is it better to just focus on the stuff you're doing right now and sort of postpone the having of ideas and the stuff, until later? Or?
Yes. First of all, let me emphasize, I don't understand what the cosmological constant is either. And second, the only advice I can offer is that you look around for something. You want to be a physicist or a scientist, find that particular line of research that fascinates you the most. Then, of course, you will find there are many things you do not understand about that line of research and about many others. You will focus a little bit and you will start to learn a small wedge of ideas in a particular direction. It certainly happened to me that, in fact, two things happened to me. One, as I moved along this direction of increasing detail of analysis of the evolving universe, I had to learn about side issues. How do stars evolve? How does the zero-point energies conspire to make a cosmological constant? The second thing is teaching. I've learned so much from teaching, from elementary courses on physics to graduate courses, because remember Samuel Johnson said, nothing quite concentrates the mind like the prospect of being hanged, right? And also, the mind is concentrated by the prospect of being shown in a lecture course that you don't know what you're talking about. You pay attention to what you're teaching, and you will learn as much as the students. But always, physics is so broad, you will never understand it all. You will understand a little bit, and you will nudge in that direction and move out slightly sideways. But first of all, and most important, be really fascinated by what you choose to do.
This one here.
You mentioned several times during your talk that ideas emerge when it's time for them to do so. Do you think we're close to the time when an idea that will help us to solve the dark matter problem will emerge?
So a time when? That would be helpful.
So, do you think we're close to the time when we'll find the idea that will help us solve the dark matter problem?
Wouldn't it be lovely? It could happen tomorrow. It may never happen. We don't know. And I think, so time and again, we have had problems that seem insoluble. An idea has occurred to someone, and we've seen a way around the problem. Time and again. That may happen with the dark matter. But we were never issued a guarantee that we'd be able to understand all aspects of reality. Do you know the example I like to give? We can be quite sure these days that there are at least as many planets around stars as there are stars in all the galaxies in the observable universe. That number is billion times billion. There is immense numbers of planets on which you can be very sure fascinating things that are happening, that you can be very sure we, the human race, will never see. That, to me, illustrates the limitations we have. We can be proud that we can make progress in understanding the world. We know we will never understand it in entirety.
One more. There's one there.
Professor, I have simply one question. Well, as we know, the light will be bent by mass. So we are located in the galaxy. So do you think the instrument or some experiments give us the truth of the universe when we observe them?
Certainly, the bending of light by the mass concentration in galaxies and clusters of galaxies is observed. And the amount of bending gives us a valuable measure of the mass concentrated in galaxies and clusters of galaxies. That's part of the game, part of the broad variety of evidence we have on the mass of the universe.
Yeah, I mean, is it possible that the universe The
You-
universe in our eyes would be like the world in the fish eyes.
I do not know about world in fish eyes.
Okay, yeah, Dicke.
Well,
Okay, let's take one more question.
I basically just have one question when it comes to the real physics and that. So, as you said, it's quite the wide subject
Yeah.
and that. But do you ever regret not going in quite a different directions in physics? Would you ever struggle to stay on your path?
It has not happened much, but I certainly can imagine being happy following another direction in physics. I followed the direction of cosmology because, well, it was suggested to me, and because I could find many things to do. But I can certainly imagine following another direction. I began graduate school thinking I wanted to do elementary particle physics. I have learned since then that I'm not suited to it. I am not a strong mathematician. I am more a visual person. I can imagine going into condensed matter physics. I can also imagine the fascination of going into the genetic code. Such a fascinating business that has proved also to be so rich. For that matter, I've always been fascinated by archaeology. Who knows?
Let's take the last question from you.
I was just wondering, like, did you ever foresee that we were going to get the Nobel Prize? And like, what do you see your role now? Like, what will you do after?
I did not foresee in 1964 that the situation would grow, the theory would grow so rich. In fact, I may say that through the years I have been surprised again and again at what can be done to check theory against observation. The Nobel Prize came at a fortunate time for me, I think. I detest self-promotion. So it's not natural for me to say this, but I think, yes, the Nobel Committee made a sensible choice.